Hi, I'm Naz Ibrahim. I'm a junior mechanical engineering major. My project tonight is going to be something related to solid mechanics. Kind of a smaller scale version of how tension and compression work in certain bridges. As mechanical engineers, we want to design bridges with the less amount of flaws. And so today we're going to test out. We have two textbook supports right here, carried along with this one style of bridge where it's just formed as almost a triangular shape right here, and we're gonna test and see how many pennies we can fit in the middle of the bridge, and if the maximum amount of pennies will fail, we'll test it out and distribute the pennies along the bridge and see how long it'll take to fail. Test one by one and see how many pennies we can place in the middle of the paper bridge before it starts having a quote-unquote bending moment. As you can see here, I put 4 pennies and the paper bridge is starting to bend in the middle. 5, making it collapse. Alright, so this time to differ the point of the load on the paper bridge, we're going to place pennies distribute them along the bridge and see if they have the same amount, if the paper goes through underneath the same compression as it would as if it was put in the middle. So we can definitely conclude that the paper didn't fail only at the distribution of pennies along the bridge evenly, but at the same time, so the same amount of pennies is pointed at the middle, or if they're distributed, it would cause this style of paper bridge, which is a triangular shaped, a rectangular shape with kind of triangular shaped moment of inertia, would cause it to fail. So previously, in the previous bridge that we had made out of the same amount of material, now we've transformed it into having several different triangular shapes in its form, and we're going to see if it will hold the same amount of pennies as it will. So previously in the bridge that we had originally designed was just based off of one triangular shape facing upwards. Now we've designed a new bridge with the same amount of material and the same exact material, but now we've transformed the shape of it to contain several triangles, so it's constantly slanted, similar to a truss. Now we're going to see if this bridge will hold the same amount of pennies or will it collapse at the same amount. So here we can picture these pennies, if you want to compare it to real life, as vehicles traveling on a bridge and seeing how much vehicles that bridge can hold. Alright, so it's definitely clear to make the conclusion that this style of bridge that we've created can definitely hold more pennies, or if you want to call them vehicles, think about it in real life, can definitely hold more pennies than the previous bridge that we have created. So the purpose of my experience tonight here wasn't to see the maximum amount of pennies each bridge can hold, but I wanted to show the viewer the difference in how much moment of inertia on a certain material can definitely affect the bending of that material. The less moment of inertia, the less amount of resistance you need by that certain beam or bridge in real life. So if you see make a comparison between these, since this bridge that can hold more pennies had triangular ridges here it definitely was more sturdy because it has a less amount of resistance compared to the bridge that we used before. It was a clear flat bridge, which isn't useful or ideal for our real life use if we were to actually design real bridges and for real life travel. To conclude this project, I also wanted to give, just in case the viewer is not aware of mechanics and how mechanics runs. So structures such as bridges are anything that can support their own weight in addition to the weight of other objects against gravity. So there's always two kinds of forces provided by weight, and that is compression and tension. So compression is the force that causes the pushing down and the tightening of the structure, and tension is the opposite of compression, that is a pull that is causing the stretching of the structure. So usually bridges are always constantly going through that in our everyday life. They're always going through compression and tension, and we as engineers have to minimize these compression and tension forces, and to minimize the flaws and the failures of our real life design. That's about it. I want to conclude with that, and go solid mechanics.